Bio students, today we're going to continue with enzyme kinetics, and we're going to start with a little review. Actually, I need to get my desk scribble back here. All right, we're going to start with a little review of topic 2 and some of the factors that affected enzyme activity, and also how you were able to calculate the rate of an enzyme catalyzed reaction. So the skill here is a review of topic 2. So if you need to go back and review this in topic 2, you may do so. So we're going to calculate and plot rates of reactions from raw experimental results. So let's review a little bit. The rate of an enzyme catalyzed reaction can be calculated and plotted according to the time taken for the reaction to proceed. So the time taken can be measured according to either the amount of product that is formed or the amount of substrate that is consumed. So think about it. If you're doing a practical experiment and you want to see how fast the reaction takes place, well, you can either measure how much of the product is formed, or you can measure how much of the substrate gets consumed. The way you measure reaction rate is by calculating the inverse of time taken. And here is the formula. Reaction rate is the inverse of time taken, so it's 1 divided by the time taken. Okay, which means that the reaction rate is higher when less time is taken, and vice versa. Right? So if it takes very little time, that means the reaction rate is higher. All right, in the PowerPoint that goes along with this, you also have a slide here that goes over topic 2.5, and it asks you to remember this. You probably did an investigation measuring factors affecting enzyme activity, and you were asked to calculate the rate of the reaction. Okay. All right, so let's look at the factors that affect enzyme activity. And again, this is a review. So pH is a factor that affects the enzyme activity. There is usually an optimal pH, but notice that the optimal pH doesn't necessarily have to be 7, depending on the enzyme, right? If the enzyme is an enzyme in your stomach, then the optimal pH is going to be much lower. If it's an enzyme that works best under basic solutions, then the pH is going to be a lot higher. The same thing for temperature, right? Every enzyme works at a different optimal temperature. If it's Taq polymerase, it's going to have a much higher temperature up here that is optimal. It might be an enzyme that has a lower temperature here that is optimal. So again, it depends on the enzyme and the condition of the organism. But notice that as far as substrate concentration is concerned, as you start increasing substrate concentration, you also start increasing the rate of the reaction. Because what's happening? The enzyme and the substrate are forming an enzyme-substrate complex, right? So that means that the substrate is attaching to the enzyme's active sites and the reaction is happening. Now there comes a point here though where it doesn't matter if you keep adding more substrates, because there's got to be a limited number of enzymes. So if all of the enzyme's active sites are taken already, then it doesn't matter if you keep adding more substrate, the rate of the reaction is just going to plateau. All right, so let's continue then. So let's distinguish between different types of inhibition from graphs at specified substrate concentrations. This is the skill. So in this skill, we're going to look at how competitive and non-competitive inhibitors affect the kinetics of enzyme catalyzed reactions. Now, one thing to remember is that they both reduce the rate of the reaction by limiting the amount of uninhibited enzyme available for the reaction. So they're both going to reduce the rate of the reaction. So before we look at how they do it, let's first look at the graph. It's very helpful. So here we see the effect of inhibition on enzyme kinetics. So on the y-axis, we have the rate of the reaction, and on the x-axis, we have the substrate concentration. Vmax is going to be the maximum rate of the reaction. So in green, you see how if you increase the substrate concentration, eventually the reaction that is uninhibited is going to reach a particular Vmax, but it's still going to plateau for the reasons that I went over here, right? So this is an uninhibited reaction. We're still going to see a plateau here for this uninhibited reaction as it reaches Vmax. Now, notice what's happening here with the competitive inhibitor. So if I add a competitive inhibitor to the reaction is still going to increase as you add substrate concentration, but it's going to increase at a much slower rate than the uninhibited reaction. And notice that even though it's going to take longer, it's going to eventually reach Vmax as you increase substrate concentration. And here is the reason why. The reason why it will eventually reach Vmax is because if you increase the substrate level, that's going to increase the likelihood of the enzyme colliding with the substrate instead of an inhibitor. So here you see you added an inhibitor. The inhibitor is attaching to the enzyme, right? So because it's attaching to the enzyme's active site, it is going to slow down the rate of the reaction here. Here it's happening at a much slower rate. But if you keep adding substrate, you have a good chance that that substrate is going to be able to attach to an enzyme at one point or another instead of an inhibitor. So the maximum rate of the enzyme activity, or Vmax, it's still going to be reached, right? It can still be achieved, although it requires a higher substrate concentration, and it's also going to require a little bit more time. Now, how do non-competitive inhibitors work? With a non-competitive inhibitor, remember what's happening here. So I'm going to draw an enzyme here, and if this is the active site and this is the allosteric site, remember that a non-competitive inhibitor is going to bind to the allosteric site and therefore change the active site of the enzyme. So even if you keep, let me move this up a little bit, even if you keep adding more substrate, right, it's not going to matter, because the non-competitive inhibitor is attaching to the allosteric site and it's changing the conformational change of the active site. So even if you add more substrate, that substrate is not going to be able to bind to the active site, no matter how much substrate you add. So notice that in a non-competitive inhibitor rate of reaction, the Vmax is going to be at a reduced level. Okay, so the maximum rate of an enzyme activity when you add a non-competitive inhibitor is therefore going to be reduced. It's going to be much slower than an uninhibited reaction. Okay, so the PowerPoint that you also have, if you scroll down to these two slides here, it tells you the features of a competitive inhibitor, right? Notice that even if you add a competitive inhibitor, the rate of the reaction is going to be reduced slightly at first, right? It's going to be much slower. But eventually, even if there's competitive inhibitors, if you keep adding substrates, you will eventually reach the Vmax. But if you add a non-competitive inhibitor, right, the rate of the reaction is not only reduced, but the Vmax is never going to be comparable to an uninhibited reaction, right? The Vmax is going to be much lower if you add non-competitive inhibitors. So make sure you also look at these two graphs. And that's it for today.